All right, let's be honest. Have you ever stared at a calculus series and just thought, where do I even start? It looks impossible, right? Well, today we're going to tackle one of those problems head on. And in the process, we're going to unlock a really powerful tool for your math toolkit. It's called the root test. Okay, so let's just dive right in. Take a look at this thing. At first glance, it's pretty intimidating, yeah? You've got these polynomials all tangled up on the inside, and then the whole shebang is raised to the power of n. So seriously, what's our first move here? How do we even begin to chip away at this? Well, believe it or not, the biggest clue is staring us right in the face. You see that little n up there in the exponent? That's everything. Anytime you see a series where the main chunk of it is just some expression raised to the nth power, it's like the problem itself is handing you a key, a very specific key. And yeah, that key has a name. And that key is the root test. Now, this isn't some general purpose tool you throw at everything. Now, think of it more like a precision instrument. It was designed for exactly this kind of problem, a series where the terms have those nth powers.
So what's so cool about it? Well, its whole purpose, its primary goal in life, is to do one thing and do it beautifully. Get rid of that pesky nth power. You know, the very thing that makes the series look so complicated in the first place. It's just a really elegant way to strip the problem down to what really matters.
Okay, so how does it actually work? Simple. We calculate a limit, and we're just going to call that limit L. The formula looks like this. We take the limit as n goes to infinity of the nth root of the absolute value of our term. And think about it. Taking the nth root of something raised to the nth power, they're perfect opposites. They cancel each other out, which simplifies everything. And once we get that value for L, it tells us everything we need to know.
And this is where it all comes together. Once you have your L, you just have to look at this table. It's super simple. If your L is less than 1, boom, the series converges absolutely. If L is greater than 1, it diverges. And if L is exactly equal to 1, well, the test is inconclusive. That just means we gotta try something else. But for now, think of this table as our roadmap to the final answer.
Okay, theory is great and all, but let's actually put this thing to work. It's time for a little case study. We're going to go all the way back to that scary-looking series from the beginning, and we're going to solve it together step by step. So here's the game plan, broken down into 5 easy steps. First, we just need to identify our term, the an. Simple enough. Second, we apply the nth root. That's the heart of the test, right? Step 3 is the magic part. The expression simplifies like crazy because that nth power just vanishes. Then, step 4, we calculate the limit of what's left over. And finally, step 5, we just take our result and compare it to 1. That's it. So when we actually apply these steps to our problem, that nth root and the nth power, they cancel out, just like we wanted. We're left with having to find the limit of n squared plus 1 over 2n squared plus 1. Now, if you remember your limit rules, when the degrees on the top and bottom are the same, the limit is just the ratio of the leading coefficients. In our case, that's 1 over 2. So, the big reveal, our limit L is 1/2. And there it is. That's our answer. We take our result, L equals 1/2, we look back at our rules, and since 1/2 is, without a doubt, less than 1, we can say with total confidence that our series converges absolutely. And just like that, the problem that looked so impossibly complex is solved. Okay, so you've seen it in action, which is great, but now let's level up a bit. Let's get into some advanced tips and tricks so you can really master the root test. This is where you go from just, plugging into a formula to actually having a strategy. Check out this series. At first, it might not look like a root test problem, but look closer. You've got 2 to the n on top and n to the n on the bottom. We can actually rewrite that whole thing as 2 over n, all raised to the nth power. And suddenly, boom, it's a perfect candidate for the root test. And when you run the test, you find out the limit L is 0. Since 0 is less than 1, we know this one converges too. Okay, here's a little pro tip for you. A limit you should probably just commit to memory. The limit as n goes to infinity of n to the power of 1 over n is 1. Why should you care? Well, because you'll often run into terms like n squared or n cubed inside your series. When you apply the root test to those, this little limit property pops up all the time. Knowing it's just 1 can save you a ton of work. All right, this is a super common question. Root test or ratio test? When do I use which? Here's a really simple rule of thumb. If you see an expression where the whole thing is raised to the nth power, Or you see something like n to the n. That just screams, use the root test. On the other hand, if you see factorials, n with an exclamation point, the ratio test is almost always going to be your better bet. Honestly, choosing the right test is half the battle.
So let's do a super quick recap. What are the big takeaways? Number 1, look for that signature pattern, stuff in parentheses raised to the nth power. Number 2, remember the root test's whole job is to cancel out that nth power. 3, the process is always the same. Find the limit L and compare it to 1. And finally, if you see n raised to the n, your brain should just light up and think, root test.
Look, the root test is an incredibly efficient, powerful tool when it works. But that leaves us with a really big question, doesn't it? What happens when it fails? What do you do when your limit L is exactly 1 and the test just throws its hands up and says, inconclusive? Well, that's where a whole new set of tools comes into play. And that, my friends, opens up the next chapter in our Journey Through Infinite series.